So let's take a detailed look at the inkjet printing head and the printability of the inks. So there are two types of printing head for the inkjet printing based 3D printing. One is thermal, another one is the piezo based ones. And if we look at the nozzle, no matter it's a thermal or piezo based nozzle, sorry. Typically the nozzle diameter is in the 10 micron level. And also, usually there are array of hundreds of nozzles in one or more rows on the printing head. Another concept is the waveform. So that is the shape of the voltage signal sent to the printing head to trigger the ejection of a droplet from the nozzle. Again, no matter thermal or piezo-based ones, they all rely on this waveform of the voltage signal. Also, the moving speed of the head usually is around 1 meter per second, and the droplet velocity is on the order of 5 to 10 meters per second. Another thing is the distance from the printing head to the substrate, and it's on the order of 1 millimeter. So it's not touching, I mean, the printing head is not touching the substrate, but it's really close to the substrate. And here shows a illustration figure of a thermal inkjet printing. And I mean, it's a little confusing of this figure because basically they flip the figure. It's upside down of the real printing head. Here, the droplet come to the upward direction. Actually, it should be go to the downward direction. But if you understand this, it shouldn't be a problem to understand the working principle for this printing head. So basically, the ink coming into this printing head through this direction, and then there will be a bubble. See, this is a bubble produced by heating up this inkjet. Basically, the liquid ink is boiled and a bubble is produced. And then the bubble, with the bubble expanding, the droplet will be ejected. So that's how the ink droplet is formed and ejected. Also, there's a conductor or resistor over here. This resistor will be heated up and cooled down in a very high frequency, such that the droplet will be ejected in a high frequency as well. Let's look at this piezoelectric ink printing head. Again, the direction is upside down. And this piezo material will be deformed if there's a voltage applied onto it. So it just like the muscle of human body, and when it is deformed like this, it will push the liquid material out of this opening and eject it to the substrate. That's how it works. And here shows the some different cases for the droplet. And as you can see here, this droplet has a long tail, right? And in contrast, this one is almost a perfect sphere. So what are the factors to affect the shape of the droplet? So basically, the shape of a droplet is dominated or dictated by the surface tension. So a low surface tension droplet will be elongated, like something like this. The high surface tension droplet will be a perfect sphere, just the one shown here. And And what kind of droplet we would like to have? Definitely, we would like to have a droplet with a shape uh, similar to a perfect sphere. Why? Let's have this illustration figure. Let's see, this is the substrate. Okay. So if a droplet like this with long tail hit onto this substrate, and this substrate will move in this direction. Let's say in this direction. So when it hits to the substrate, and it will be something like this, because it has a long tail and this motion. So there will be a streak formed in this case, which is undesired, because with this streak, it's hard to control the printing accuracy and the dimension accuracy. So definitely, we don't want to have a droplet like this, and this is a preferable ones. Also, for the main manufacturers of the material jetting systems, like the Stratasys, they use the Recon printing head, and the 3D system use the Xerox printing head. And these are really expensive. You can see the price for each of the head could range from several hundreds to a few thousand, which is really expensive, right? So some other features for the printing head. So first of all, the printing head is in a vacuum condition. Why we need a vacuum over here? That is because we would like to prevent the liquid from oozing from the nozzle. That means if there's no driving by the thermal or the piezoelectric forces, there shouldn't be a liquid leaking from the nozzle. So basically, if we put vacuum, that will be prevented. Another thing is we want to have a capping station. Means if we don't use the printer for a long period of time, we definitely want to put a cap to the nozzle, because if we do not do that, the printing head will dry out, and it cannot be restored. Considering the cost for each of the printing head is like very expensive, few hundred to few thousand. So you definitely don't want to do that, and that's why the capping station is necessary. Another thing is the straightness of the jetting. Of course, you want to have the printing head in straight towards the substrate instead of in some tilted angle like this, right? That's another thing. And the first point is this drop velocity, right? And this drop velocity is controlled by the voltage signal. Just imagine if the drop velocity is too fast, what's going to happen? When the droplet hit on the substrate, there will be splashing generated. Then the printing accuracy cannot be controlled. So that's why we do not want to have a too fast velocity for the droplet. Also, the droplet volumes. The volume is related to the amount of material to be ejected each time, and it turns out will again affect the printing accuracy, how much material there, and the dimension accuracy as well. So as you can see here, there's a introduction about the resolution of the printing. So basically, there's a concept, we call it dot per inches, or in short, it's DPI. It measures per unit inch how many dots will be jetted over there. And another thing is the spacing. So the spacing is kind of an inverse of the resolution of the DPI. Basically, it measures what's the distance between the two dots. So if you know the DPI, let's say you have DPI on 1,600, that means per inch you have this amount of dots. Then the distance between the neighboring two dots will be the inverse of this, right? But that's not in the micron. It's in the inch, right? Then you need to convert this to a micron unit. Then you will have the spacing. So again, these two values are the inverse to each other. Okay. Another interesting computation related to the inkjet-based material jetting is the volumes and the diameters of the droplet. So we can assume we have a perfect droplet. That means it's a sphere, right? That each of the droplet is a sphere. Then we have the equation for computing the volumes of a sphere, which is something like this. And if you know the droplet volume, which is the 30 picoliters, that means you know the V in this time. And what is the diameter of this droplet? Then you could substitute the volume value over here and compute this radius. This is not a diameter, it's a radius. And then times 2, then you will have the diameter of this droplet. So another concept is called the nozzle pitch. So the nozzle pitch represents the spacing between the nozzle on a printing head. That means this is the printing head, and there are a series of nozzles. And what will be the distance between each of the two neighboring nozzles? And again, this nozzle, this printing head will move in this upside down, up-down direction, right? So if you know the whole width of this printing head, and you know how many nozzles along this width, you could easily compute the spacing between the two, right? Another thing is, how about the distance between the two droplets in this direction versus the one in this direction? Are they the same? I think that we mentioned this a little bit in the previous slides. So actually, they are independent to each other, and the distance, the spacing between the two droplets in this direction actually depends on the moving velocity of the printing head and the frequency of the droplet. And we will go to details later. So as you can see here, we for the droplet spacing, there could be different cases. For example, there could be multiple paths for jetting the droplet. For example, in the first pass, you just drop your droplet like this, right? The material like this. And then in the second pass, you just offset this printing head in this direction a little bit, and then do another material jetting. And it turns out you will have this line of material and this line of material have little overlap regions, such that you could have different control on your printing. And also this offset distance between the two nozzles, this distance could be like one half of the nozzle spacing in this direction, or 1/3, 1/4, and so on and so forth. Depends on how you want the printing patterns look like. Okay. So as we mentioned, if we have a if we have printing head moving velocity, which is v in the unit millimeter per second, and you have a frequency, droplet frequency f, which is in the unit drops per second. So how you compute the drop spacing? That is the distance. Let's see, you have a, maybe I draw here. You have a printing head, and you have each of these nozzles, and it move in this direction in the velocity v, and the droplet velocity, frequency is f. Then what is the drop spacing in this direction? So that actually that's not difficult to derive. I will show you how to derive it. So first of all, the final the droplet spacing is in the actually it's in the unit of a micron per drops, right? That means you have to convert this velocity to which is in the unit millimeter per second to micron per second. Then what you want to do is just time 1 micron, 1000 micron per millimeter, right? And then you could over this to over the frequency, which is in drops per second. Then you could cancel out the second and cancel out the millimeter here. And no, it's here. The micron should be remaining. And turns out you will have the drop spacing. In this direction, in the unit micron per drops. That's how you come up with the drop spacing v over f. Of course, you need to do this unit conversion. Of course, if there are different units, let's say you have a inch, right, inch per second, or centimeter per second, you need to do the conversion of the unit as well to make sure what you have will be the correct drop spacing. All right. So another important topics is this printability of the inks, and there are a few fundamental properties of the ink which related to or governing the printability of the ink. So first one is the viscosity. So this viscosity measures how easy the ink flows through a small diameter of nozzle. And the second concept is the surface tension. And the surface tension will decide what's the shape of the droplet, as we mentioned previously. It's is it a perfect sphere shape or a elongated teardrop shape, so on and so forth. And another concept is the inertia. So this inertia is basically measures the energy of the droplet provided by the either the thermal or the piezoelectric forces. And there are a few characteristic numbers. One is the Reynolds numbers. So the Reynolds number is something like this. I don't want to go to too details, but it represents, it gives the ratio of the inertial forces and viscous forces. So when smaller Reynolds number appear, that means the viscous force dominant, and it will lead to a laminar flow. And a high Reynolds number means the inertial force dominant and lead to a more turbulent flows. Right. Another characteristic number is the Weber numbers. Basically, that's the ratio between the initial force and the surface tension. And a high Weber number will lead to a droplet splashing and break up on the substrate. And the lower one lead to a droplet that land on substrate and contact. So definitely you want to have you want to have an appropriate Webb number and Reynolds numbers. Another one is this Onsurge numbers. So the Onsurge number is a combination of the Reynolds and Weber numbers, and it removes the influence of a droplet velocity. And something like this, you can look at. Actually, for the printability of certain ink, definitely you want to look at this very interesting graph. Basically, the horizontal axis is the Reynolds number, and the vertical one is the Onsurge numbers. And basically, the focused region should be like this. That means once the ink, if you compute both the Reynolds number and also Onsurge number, and it follows into this region, that means it has a very good printability, and it could be used for the manufacturing, the 3D printing process. So any region above gives you a fluid with too high viscosity, and anything below here gives you a satellite droplet. This satellite droplet is the droplet which is much smaller than the regular droplet it should be, right? And if any region on the left of this line, that gives you the insufficient energy for the droplet to form. And if you are talking about the region right-hand side of this line, that's the splashing. There are too many inertial energy there, and you will have a splashing. Basically, the droplet moves too fast, right? So with understanding of this graph, you could have some information about the printability of the inks. So here shows you some online tools. Basically, once you input the material properties of certain ink, it will compute all these characteristic numbers as well as give you a printability regions. Right? You could take a look at it. So basically, by using all these known factors of a ink, you could compute the width of the bead. So as you can see in this one, from the leftmost shows a bead which have too little overlap. So each of the droplets separate with the neighboring ones, and it's not a good line formed. And for the rightmost one, there are too many material jetted. There are too many material overlap to each other, so you will have these regions as well. And I would say this one is a perfect line formed by the material, and this one is almost perfect, right? It's much better than the leftmost one. And definitely that's the one we would like to pursue for the printing. And it could be evaluated by looking at this equation. All right. So